Hello and welcome back to module number 7, and this is going to be hard because this is basically the essential of statistics, and we are going to try to cover it by looking at two parts. One is the how do we provide interpretation of the confidence interval estimate for the mean, and second, how do we determine the sample size necessary to develop the confidence interval for the mean, or, and again, or the proportion. So I'm going to talk about a lot of things, and I hope you'll be able to ask. Again, if it's not clear, please let me know so I'll be able to slow down or give you a more scaled down presentation in order for you to understand it. But this is what I want you to get out of it in order for you to understand why is it so important to estimate the population mean, what is the population proportion, and how do we determine the requirement sample size. Why is it so important? Again, this is part of our calculation and how we apply that. I will end up again giving you an example. How do we do that in R? But the first objective that I had in mind is, in this case, that you will be able to do that, not only understand the procedure, but also to understand the framework that we are working with. So let's start with the basics. The point estimate is a single number. The confidence interval provides additional information about the estimate. So the point estimate, but we have a lower and a upper confidence limited that give us the proportion in order for us to do that. And when we have the point estimate, we can estimate the population, and when we have a sample statistic, a point estimate, we estimate the proportion doing different ensemble. So in this case, with the sample statistics, a point estimate, we have a X bar in compared to when we estimate the population, we usually use the mean. So this is where we start the discussion about confidence interval and how much certainty is associated with the point estimate of the population, and how do we calculate that in the overall thing. So the confidence interval estimate, we are trying to establish or take into consideration in a sample statistics from the sample to a sample. So it's based on one sample, giving them information about the closeness to unknown population, and it states in terms of level of confidence: 95% confidence, 99% confidence, but we cannot ever say we are 100% confidence in our result. So the confidence interval example: if the population has a mean of 368 and the standard deviation is 15, we are following the following procedure. We have to know the n, which is the number of cases, and in this case, this is how we contain the 95% of the sample mean. And when you do not know the population mean, you use the X hat and to estimate the mean, and in this case, this is the procedure that we do in order for us to find it. So in this case, this is where we come up with the idea of X hat, and lower limited, upper limited, contain them if you have the mean in this case, and when you don't, this is where it comes from. I hope it makes sense. However, in order for us to calculate the internal confidence interval, we have to add into the consideration the use of the z, and I will talk about that in 2 seconds. But the practice you will take is one sample of size n. In this practice, you will also do not know what is the mean, and you do not know what is the actual interval actually containing the mean. So, however, we do not know that 95% of the interval form in this manner contains the mu. So this is based on one sample that actually selected you can be 95% confident your interval, and which is the mu in this case is 95% confidence interval. So the estimate process, when you have a random sample and the population in this case is the mean, the mu is unknown, and so in this case I need to find that in this case that 95% confidence that the mu is between 40 and 60 in order for us to do that. In this case, as a result, the x hat is equal 50. So how do I do that? How do I know all of it? Again, the issue of point estimate. It's plus minus critical value and the standard error. The point estimate is the sample statistic estimate of the population in this case. The critical value is a table based on the sample distribution of the point estimate and the desired confidence level. The standard error is the standard deviation of the point estimate. So in this case, the confidence level is the confidence when we contain unknown, and usually it's less than 100%. So suppose confidence level is 95%, also written as 0.05, and the idea here is how do we calculate in order for us to do that? When we are talking about confidence interval, we usually talk about known or unknown and the population mean and the population proportion. This is where the confidence interval comes into play. When it's known, the population standard deviation is known. The population is normally distributed. If the population is not normal, we usually use a larger sample size in order for us to overcome this idea. So the confidence interval estimate contains the following formula, and now it's really important. In this formula, the x hat is the point estimate, the z-score in this case is the normal distribution critical value of the probability when we have to follow the following calculation in each trail, and we also need to calculate the standard error in that case. So that is the formula that we are trying to calculate when the mu is known. And how do we do that? In this case, I illustrate the following example. And again, the idea is that we have normal distribution. We also, as I said before, we have to have some value in order for us to do that. And in this case, this is where the values come into play in order for us to do. So again, I try to illustrate to you how it play out in this case and what does it means. And let's take an example. And again, the example illustrate the values that we need to determine if 95% of confidence interval for the true mean is reflect the population or not, and that's really important with regard to establish. So we have an example, we have the mean, and we are trying to know what is the past testing of that population standard deviation in order for us to establish that, in order for us to know that. So the interpretation of this type of calculation will give us that 95% confidence that the true mean resistance is between 1.9932 and 2.4068. Although, and I repeat again, although the true mean may or may not be the interval, 95% of the intervals formed in this manner will contain the true mean, and this is where it is known. But what do we do when it is unknown? And so this is a problem that we will need to face, and we will do that later on. But the foundation or the framework for that is that, do you ever truly know the value of it? Probably not. And if there is a situation where the Q is known and then the mu is also known, and since the calculation, you need to know the mu. So there is connection here that we will establish it, and we will present the solution after that with regard. But I'm going to turn over now. I talked about a little bit about when is known and unknown, but we also need to talk about population proportion. And in this case, the confidence interval for the population proportion, and again, the interval estimate of the population can be calculating by adding the allowance for uncertainty to the sample proportion. And in this case, we are recorded. I want you to record the distribution of the sample proportion, and we will estimate this with a simple data in this case. So in this case, the upper and lower limits of the population proportion are calculated with this formula. The P plus minus the Z multiplied by the Q divided by 2, and the square root of P multiplied by 1 minus P divided by N, and it's all square root. So let's take an example. The random sample of 100 people show that 25 of them are left-handed. So from 95% confidence interval that the true proportion are left-handed, in this example, what can we apply and what can we learn about that? So from the 95%, we can assume that 0.165 to 0.3349 is where the proportion is laid out for us in this case. So the interpretation is that we are 95% confident that the true percentage of left-handers in the population is between 16.51% and 33.49%. Although, and again, although the interval form of 0.651 to 0.3349 may, and I repeat, may or may not contain the true proportion, the 95% of this from the sample of 100 in this manner will contain true proportion in that sense. So that leads us, how do we determine, how do we came up with 100? Why? How do we do that? So in this case, when we are determining the sample size, we need to know for the mean and for the proportion. But we also need to be considered with a sample error, and the requirement sample size can be found with a desired margin of error with specific level of confidence. So the margin of error is also known as sample error, which means that the amount added or subtracted to the point of estimate from the confidence interval. So when you are determining the sample size, you are talking about the mean, and this is the formula that we calculate. And when we are determining the sample size, this is what we come up with. So to determine the requirement sample size for the mean, you must know, again, the desired level of confidence, which determines the critical value of the z, and the acceptance sample error, and the standard deviation. So an example, and again, I give you all the premises of this example in order for you to say that, so the requirement sample in this case is at 220, even though the calculation is more accurate saying that it is 216. I always round up in order for me to, again, make sure that I have the actual number. But when it is unknown, what do we do and how do we apply that in that sense? So when we are determining the sample size, this is for the proportion, this is the formula that we got in order for us to apply for that. So to determine the requirement sample size for the proportion, we need to know the desired level of confidence, which determines the critical value of the z, and we need to have the acceptable sample error and the true proportion of the events. And the idea here is that the requirement sample size example in this case within plus minus 3 within 95% confidence, assuming that a pilot will have p equal to 0.12. So how do I do that? How do I pursue that? And in this case, I plug in the numbers that I have with this formula in order for me to get these numbers, in order for you to find that the use of n is equal 451. So the confidence interval for the population total example, and again, this is an example that I want you to follow in order for you to have better sense what it is, how do we apply that, and how to do that. Of course, there is the question, how do we apply that in R? So let's go back to what we covered and so far with R. The mean with the standard deviation in R is usually the application called g-norm. The mean with a standard deviation using the summary statistic in R stands for qt. The mean with the standard deviation of unknown using R is t.test, t-test. And the proportion of using statistics in R, again, is q-norm. So example, in this example, I have some container contains some salary, and in this case, the salary when you will graduate from our program. So 90% of the people and 90% and 95% confidence interval from the mean. So in this case, I was able to calculate the standard deviation and the mean in order for us to do that. The foundation, but that leads us to the foundation of hypothesis testing. Basically, what we did here is the foundation of the hypothesis testing. So it is what I will cover in this case. I will cover one sample test in order for you to do that. So in this presentation, I will talk about the null and the alternative hypothesis, about test statistics, the p-value, the significant level, one test z-test, and the power and the sample size as we covered before. So the terminology that I'm going to use in this section is the population of all possible values, the sample is the portion of the population, the statistical interference is the generalization from a sample to a population, calculate with a degree of certainty, and the two forms of statistical interference, the hypothesis testing, the estimation, and what we have about the characteristic of the population and the characteristics of the sample in this case, and how do we calculate. Remember that when we are talking about the sample, it's usually is the x hat in those terms. So the distinction between those two things is, again, the source. In this case, we are talking about population versus a sample. The notation is, in this case, is the mu. In sample, we are talking about the x bar, and the in the entire population is not. In a sample, it is yes, and the calculate no. In the sample, we do. So again, this is the procedure that we try to apply. We are trying to apply the sample onto the population in order for us to do that. So what is a hypothesis? And this is really important. It is a claim about the entire population by taking a sample out of it. The population means, example, the mean monthly cell phone bill in the city, and it's equal to 42. The population proportion is that proportion of the adults in the city with a cell phone is 0.68. We also need to know what is the null hypothesis, which state or claim to be tested. We are testing the null hypothesis in order for us to verify or accept or reject the hypothesis. So the average, again, it's all about how do we apply that, and do we apply that. In this case, the null hypothesis is usually marked by age 0, and if it's true, or is it false. So begin with the assumption that the null hypothesis is true. Similar notation of innocent until proven guilty. So the reference of the status quo or historical value always contain the idea of or, smaller or equal, and we may or may not reject the result. The alternative hypothesis, which is marked by H1, is the opposite to the null hypothesis, and the average is, again, the idea is the challenge of the status quo. It never contains equal or smaller or bigger. It may or may not be proven, and it generally the hypothesis research is trying to prove. So this is what we are trying to prove as true. So the hypothesis, a testing process, a claim about the population average age is 50, and so the sample to population of the to find the sample mean. And again, the sample needs to be representative by the entire population. So in this case, suppose the sample mean age is equal 20, and the significant lower than a claim of the population age of 50. If the null hypothesis were true, the population probability of getting such different sample mean would be small, so that you can reject the null hypothesis. In other words, getting the sample mean of 20 is unlikely if the population mean is 50, so you can conclude that the population mean must not be 50. So in this process, we are trying to, again, see if the null hypothesis is true, and if it is, we can reject or accept or need to accept the null hypothesis, and that's where we come into play. The idea of finding the critical value is the sample mean is close to the state population mean, and the null hypothesis is not rejected. If the sample mean is far from the stated population mean, the null hypothesis is rejected. How far is enough? Again, the issue of the critical value is where we determine this answer to this question. So again, the t-statistics and the critical value, in this case, this is too far from the mean of the sample distribution, and how to do that. We also, in the hypothesis, we have the idea of how to overcome error or test decision making. We have type 1 and type 2. Type 1 error is the reject the true null hypothesis, considers a serious type of error. The probability of type 1 error is usually calculated and measured, usually called level of significance of the test, and it said the researcher in that setting. Type 2 error is failure to reject the false of null hypothesis. If the null hypothesis is false and we not reject it, it is a type 2 error. The probability of type 2 error is marked by the notation of B. So again, summarize the possible errors in testing, hypothesis testing. In this case, do not reject or not reject, and how to apply to it. So the confidence, I want you to go over that. So this is part of the equation that we need to make sure that we follow in order for us to do that. And there is an idea of relationship. Type 1 and type 2 error cannot happen at the same time. And so if type 1 error cannot occur if the null hypothesis is true, and type 2 error can only occur if the null hypothesis is false. And factor affecting the type 2 errors, and again, this is something that you need to consider in order for you to do that. The hypothesis test for the mean, in this case, when we know the z-test and we are trying to establish it, and again, the z-test of the hypothesis of the mean, in this case, this is the starting point when we know the value and when we do not know the value. So the critical value approach to the test is to convert the sample statistics, the z hat, to a test. And if the test fails the rejection, to reject the null hypothesis, otherwise we do not reject the null hypothesis. To trail test is that there are two cut off values defining the region of the rejection, and in this case, in this graph, you have the lower critical value and the upper critical value, and in between we do not reject the null hypothesis. So there is 6 steps, and I want you to have a very clear steps on it. First, state the null hypothesis, state the null hypothesis, and state the alternative. Choose the level of significance and the sample size. Determine the appropriate test and the sample distribution. Step number 4 is determine the critical value that divide the region and non-region values. Collect the data, compute the value of the test, and make statistical decision. Test the test fall into non-rejection. Do not reject the null hypothesis. If the test statistics fall within the rejection region, reject the null hypothesis. And again, make sure that you are transparent with your procedure. An example. Again, this is example of the test, and I lay out for you what is my null hypothesis, what is my alternative hypothesis, and how I'm supposed to test it in this case. So I'm starting with a specific claim or hypothesis. I'm giving a symbolic form. I give 2 value of expression that giving me the idea of what is the value of the null hypothesis. And again, the identity of the null hypothesis in this case is greater than 0.5, and when the mean height of professional basketball is, example, most 7 foot tall, and or the standard deviation of IQ score of actors is equal 15. In this case, this is what I need to do in order for us to do that. Again, example of the no and an alternative. How do you phrase it and how to apply to it? I want you to go over that, and I will give you an assignment that is connected to this. So this is it for this time. I know I cover a lot of ground in this presentation. Please ask question if it's not clear. I will provide more information. Until next time, have fun.